Thank you very much.
No problem. So last time we covered the auto cycle and we talked about all the characteristics of auto cycle. And I also lay out how we basically approach solving auto cycle problems. Now this time I'm going to do the example. Please, if you have your textbook, make sure you have table A17 with you. For those of you that you have an e-textbook, I highly recommend that you guys print A17 and A17E. These are the Airtable for SI unit and English unit. Have it handy because you're going to need it when you're taking the exam. And that's very crucial to have it with you when we solve problems here at the board, so you can follow and kind of practice how to read the tables and where everything's are. If you don't practice that and don't get the hang of it, you're going to have major issues and major problems down in the road. So please do that. If you have a textbook, that's simple. Just have your textbook next to you and have it handy so we can follow. You can follow what I'm doing here. Now, okay, I'm missing 4 people. Is Mr. Lai, L-I, is he in? No. Okay. Now, the example of auto cycle, I'm going to just draw the equipment diagram and I'm going to erase it. So again, we have this compressor. Air is going to go into a compressor at point 1, coming out at point 2, going to the combustion chamber, introducing the fuel. Then we come out at point 3, going to an engine, coming out at point 4. Now we can connect back to the heat exchanger to get the first point, and that goes clockwise. Again, to refresh your memory, this is what the work we put into a system. This is the work we get out of a system. This is the heat we add into the system, Q in. And this is heat that we remove the system to get from point 1 to point 4 to point 1. That completes the cycle. In auto cycle, you're required to draw both TS diagram and PV diagram. Again, just refreshing your memory, doing the TS diagram, we said all compression and all expansions happen isentropically. We have one compression here, one expansion here. So this is going 1 to 2 isentropically. And then we have 3 to 4 isentropically. Connecting these two, that gives me the TS diagram. The heat added to the system and rejected to the system, it happened at constant volume. So we have 2 to 3, 2 to 3, that's our Q in, and 3 to 4, I'm sorry, 4 to 1, that's our heat rejection. That completes our TS and PV diagram. Again, not to make any mistake, 1 to 2, 1 to 2, isentropic. So I will dash this way I won't make mistakes. 3 to 4 is isentropic. So we cannot solve problem without having the TS and PV diagram in this, auto cycle. Now here, this is the work in. This one is work out. Q in and Q out. Similarly here, this is Q in. This one Q out. This is the work we put into the system, and this is the work we get out of the system. Now that we have TS and PV diagram, we really don't have any need for the equipment layout. Is it okay if I erase it? Because nothing has changed. You've seen this so many times already. Okay. Now, the example. We have an auto cycle that the compression ratio is equal to 8. So R of V is equal to 8. And we know that that is equal to V1 over V2. I write these because I won't make any mistakes down the road. Then it says, at the beginning of the compression, where is the beginning of the compression? 0.1. So that means T1 is equal to 27 degrees Celsius. I automatically add 273 to make it 300 degrees Kelvin. Pressure at 0.1 is 95 kilopascal. Then this is a trick. That's why I said you need to read the problem very, very slowly and very carefully. Now, it says that we're going to add 750 kilojoule per kilogram heat to the system. What does it mean? Our Q in is already given to us. So Q in is given to us to be 750 kilojoule per kilogram. What is Q in? If you recall, Q in, this is a constant volume. So that means is U3 minus U2. So I just write the equation in front of it because I'm going to need it later. These are the things, these are the tricks that you can use to help yourself solve the problem very quickly. So it says 750 kilojoule per kilogram of heat is transferred to the system at a constant volume. We already know that because that's the definition of auto cycle. Consider variable speed, specific heat. When they say consider variable specific heat, that means CP and CV are not constant. It says variable, that means that they are varied with temperature. So they're not constant. Right off the bat, they're telling us. Now, these are all the information we have. They ask us to find the following. Find T2 and P2. Temperature at point 2 and pressure at point 2. That's A. Part B, asking us to find the network. What is the network? Network is equal to Q in minus Q out. That helps me to understand what are the parameters I need to find. Part C, thermal efficiency. What is thermal efficiency? Network divided by Q in. Finally, find MEP. What is MEP? Is a network divided by maximum volume minus minimum volume, V1 minus V2. So these are the 4 things that we need to find. These are all the given information. We have TS and PV diagram that's going to help us as we go through solving the problem. Any questions before we start?
Is this example from the book?
No.
All right.
Any other questions?
Professor, please, what does part D say?
Part B says finding a network.
Oh,
And a
sorry.
network we know is Q in minus Q out.
Oh, sorry. I said part D.
Oh, D, I'm sorry.
Oh, thank you.
It's MEP, mean effective pressure.
No.
Mean effective pressure is a network divided by V1 minus V2.
Thank you.
By maximum volume minus minimum volume. Is that okay?
Yes, thank you.
No problem. That's what I'm here for. Any other questions? Okay. To start with, we need to find T2 and P2. I can very quickly find the pressure at point 2 because I have everything. And I'll show you, let's see, solution. I know there's an equation for ideal gas, T1 V1 over T1 is equal to T2 V2 over T2. I have V1 over V2, not a problem. I have P1 and T1. I need to find the value of T2, then I can easily find the pressure at point 2. So I leave this and go back to it when I find the value of T2. So I got the state 1 at 300 degrees Kelvin. I go to table A17. Please, if you have that, look it up. I will find the following 2 values. Sorry, I'm going to need this space. U2 and T2 from the table. Sorry, my bad. U1 and VR1. Now, if you look at the table, you find the value of U1 to be 214.07 kilojoule per kilogram. For those of you that you have your textbook, do you see this number? At 300 degrees Kelvin, go to this table, see if you can find the value of U1. How many of
Yep.
you have the?
Yeah, that's what I see.
Yep, I
Yeah,
found it too.
got it.
Yep.
All right, glad to hear that. Now, tell me what is the value of VR1?
621.2.
Right here. Relative volume doesn't have any unit. So leave it alone. Don't forget, numbers without unit are meaningless. U1 is an energy, has a value of kilojoule per kilogram, the unit mass. That's why I put it there. This one doesn't have any units, so I'll just leave it the way it is. Now we go to state 2. I'm going to write VR1 over VR2 is equal to V1 over V2. That means 621.2 over VR2 is equal to 8. So if I divide this number by 8, I get the value of VR2. So VR2 becomes 77.65. Now I'm going to go backwards on the table. So I'm going to say add VR2 equal to 77.65. I go to table A17. Now I find U2 and T2. Now this is a trick. At this point, when you look at your textbook, you don't find this value that you can just go across and find U2 and T2. What you need to do, you need to interpolate between the two numbers. You find the lower number and higher number, when 77.65 is right between them, you interpolate and find the actual value. Now, when it comes to the test, I don't want you to do that because that's a waste of time. Again, remember, we're not here to have an accurate answer. We're here to be at least in the ballpark. So what you can do, you can make assumptions. Look at this value, look at the closest number to this, and then write, I assume U2 is equal to that and T2 is equal to that. Good enough, and move on. But as far as the homework concerned, I expect you to do the interpolation because you have plenty of time. In the test, I allow you to make that assumption. However, if you are not within that boundary, if you get you assume a number that is way out there, that's not going to work. So don't think because you wrote your assumption, therefore you'll be okay. As an engineer, we always make this kind of assumptions. That's going to be our future. However, our assumptions are pretty close to the reality. We don't make assumptions that is completely out of whack. What kind of engineers we're going to be if we do that? So as we get close to the test, I'm going to give you some examples. You get the hang of it. when times come. For now, you don't have to worry about it. Now, if you do the interpolations and all of that, you find out the U2 value would be 491 kilojoule per kilogram. And the temperature at point 2 becomes 673 degrees Kelvin. Now, I want you to look at the table. Do you see these two numbers? You're probably not. But if you look at the VR2 higher than 77.65 and lower than 77.65, you see these two numbers are right between those two. And that's all you need to know. That's all you need to do. Any questions?
Yes. Did you get those numbers via interpolating, or did you just pick
No,
pick
these
numbers
are
that were very close in between the two?
These are the accurate numbers. I use a computer software to do that, which you don't have access to. But if you do interpolate, you get something close to that.
Okay, gotcha. Thank you.
No problem. Any other question? So, are we done with state 2? Not yet. Part A of a problem, we already took care of it. That's temperature. So I go back to this ideal gas equation. P1 V1 over T1 is equal to P2 V2 over T2. What happens if I divide both sides by V2? I will get P1 times R of V divided by T1. On the other side, I will have P2 over T2. Is that correct? Because if I divide both sides by V2, this becomes V1 over V2, which is R of V that I have. P1 is given, T1 is given, T2, I just found it. What's unknown in this equation? P2. One equation, one unknown. So from there, I will find the value of P2, the pressure at point 2 is 1704 kilopascal. So I found my U2, that's what I need. I found my U1, that's what I need. And I solved part A of the problem, finding the temperature and pressure, and then end of a compression process, right there. Any questions? Okay. Now, yes.
Sorry, the P1 times, is that the ratio?
This is the compression ratio.
Compression ratio? Yeah. Okay. Thank you.
You see, if I divide both sides, this becomes V1 over V2. If I divide both sides of this by V2, this will cancel. This becomes V1 over V2. What do we call V1 over V2? R of V. And that's what I put it there.
Thank you.
No problem. So this is, now, before we go further, if you remember when you're solving a problem at any given point, you can look at your answers and see if it makes common sense. If it doesn't, that means you've done something wrong. We start at an ambient temperature of 27 degrees and 95 kilopascal. We're going to point 2. Look at our temperature. More than twice. That's what it's supposed to be. Look at our pressure. 1700. That's about almost 20 times. That's what happens when we compress the air. That's the work of a compressor. So it makes sense. We're in the right track. We're doing great. That's how you can check and don't keep on going until you get a crazy answers. Again, if it doesn't make common sense to you, definitely you have made a mistake. If this number is T2 lower than T1, that's impossible. T2 has to be higher than T1 on the TS side. Pressure-wise, look at that. This is P1 right here. That's P2 right up there. It has to be bigger. So you're okay, you're in good shape. Now we go to state 3. I look at the state 3, go back to my problem, see what do I have. Q in, which is U3 minus U2, is given to me. So I'm going to write 750 kilojoule per kilogram is equal to U3 minus U2. U2 is right there. This is Q in, it's given to me. One equation, one unknown. So I find the value of U3. My U3 becomes 1241.2. I'm sorry, I forgot to put 0.2 here. So that kilojoule per kilogram, that's the third value. So all I have to worry about finding U4. Now, I'm going to erase the given part. Is it okay? Are you okay with that?
Yes, Professor.
Yeah, I'm good.
Okay, thank you. So I'm done with the state 3. If the problem would have, I'm sorry, I'm still haven't done with the state 3. My bad. Now that I have U3, I say at U3 equal to 1241.2 kilojoule per kilogram, I go to table A17 again. This time, I can find T3 and VR3. Once again, if you go to the table, you don't see 1241.2. Again, you have to interpret, which in the test, you're going to make assumptions. Now, when you do that, T3 becomes 1539 degrees Kelvin. And VR3 becomes 6588. Again, we have temperature, we find U value, VR value. We have VR value, we find U value and temperature. Now I have U value. I can find the other two parameters, temperature and VR3. So that's how you keep going back and forth. You need one of those values to find the other two. Very simple.
Professor?
Done with the state 3, so I go to state 4. At state 4, I write VR3 over VR4 is equal to V3 over V4. I replace V3 with V2 because they're the same. That becomes V2. What is V4 equal to? V1 over V1.
Professor,
I see this is a 1 over R of V. And R of V is given to me, that is 1 over 8. So now, VR3 was 6.588 divided by VR4 is equal to 1 over 8. That means if I multiply that by 8, I get the value of VR4. So the VR4 value becomes 52.7. Now, I say add VR4 equal to 52.7. I go to the table A17 and find U4 and T4. The problem didn't ask me to find T4, so I'm not going to bother with that. Why should I do extra work? All I need the value of U4. In this case, after interpolation and everything, this becomes 571.7 kilojoule per kilogram. Whoops, I'm sorry, 571.7. If you're interested to know what that T4 value would be, is 774.5 degree Kelvin. We don't need it, but I just give it.
Professor,
Yes,
I had a question. Their light is kind of blocking on state 3, the answer to T3.
answer to T3.
Yes, on state 3.
The answer to temperature T3 is 1,539 degrees Kelvin.
Thank you.
Not a problem. And again, if you check, look at the temperature at point 2 is only 670. Look at this one, it's 1540. That's what it's supposed to be. Because we add heat, our temperature is going to go up. Look at the pressure. If we wanted to find the pressure would have been twice as that, 1704. That's a very high pressure. Now, if I look at my state 4, all of a sudden, my U4 dropped, my temperature from 1500 comes to almost half of it. So now I better bring it back to point 1 through that heat exchanger. So I went around the cycle step by step and find all the values that I need. So in order to get the network, which is this one. So part B is a network equal to Q in minus Q out. In this case, Q in was given to us, so I don't have to do anything. What is the Q out is equal to? That would be 750 kilojoule per kilogram minus Q out is U4 minus U1. Q out, U4 minus U1. That's what I have here. I have the U4 right there. I have U1. This is given. So network becomes very simple. So I have network value be 390.4 kilojoule per kilogram. That means this cycle would give me that much power. That's what I'm after. The network, not the W out. I'm after the network for the whole cycle, not just one component of it. So that was part B. Now we go to part C. Part C is thermal efficiency. That is network divided by Q in. This is given. This one I just found. So if I plug the number in, I will get the thermal efficiency of 52.39%, or generally we say 52.4%. That is efficiency of our cycle. That's part C. Now let's work on part D problem. Okay. If you don't mind, I want to erase these so I can put it up there so everybody can see that. Part D, asking for mean effective pressure. That is equal to network divided by V1 minus V2. Now I have a problem. I don't have the values of V1 and V2. What do? Okay, I go back to ideal gas relationship. T1, V1 is equal to R T1. T1 is given, T1 is given, R is a universal gas constant that I can find it from air table. What's unknown here? Just the V1. So if I plug everything in, by the way, the value of R is 0.287 kilojoule per kilogram per degree Kelvin. Just the number if you want to put it there. T1 is 95, T1 is 300. Very quickly, I can find the value of V1 to be 0.906 meter cubic per kilogram. That's the V1. So if that's a V1, what is V2? V2 is equal to V1 over 8. Because V1 over V2 is given to be 8. So if I divide that number by 8, I get the value of V2. So now I have everything in that equation. MEP is equal to my network, 390.4 kilojoule per kilogram, divided by V1, which is 0.906 minus 0.906 divided by 8. All I need to do is just calculate that number. I'll end up with mean effective pressure of 495 kilopascals. That's part D of the problem. The entire trick into this, again, number one, take 1 minute extra time, read the problem very, very slowly and carefully. see what you have, what you don't have. Write all the things that you have, and to help yourself, just write the equations that you know next to it, because they come handy. Then write things that you need to find. Also, write the equation next to it so you know the parameters that you need to find. Then start with the state 1, complete that, go to state 2, complete that, go to 3 and 4. Once you get there, you have all the values around the cycle. Then you can find Q in, Q out, network, thermal efficiency, MEP, everything that the problem will ask you. So that's the trick, or that's how we do solve problem in thermodynamics. The beauty of doing it this way, as you notice, at any given point, I keep checking my answers. See if I'm in the right track. If I find any weird numbers, because when I was punching it in my calculator, I punch 8 instead of 5 or 2 or whatever, then it becomes so obvious, you know, you made a mistake. So within a few seconds, you can go and correct it. But if you let it go too far, then you have a tough time to understand where you made a mistake. And when you end up here with the efficiency of 10%, then you did something wrong. If you come up with the efficiency of 98% or 99% or even 1.1%, again, you've done something wrong. But you don't know where you made that mistake. And you don't have time to go through the calculation to see where was it. But if you take just 10, 15 seconds, use your common sense, forget about thermodynamics, forget about engineering, forget about everything. Common sense tells you from point 1 to 2, you increase the temperature, you increase the pressure. Common sense tells you when you add heat to the system, at point 3, you increase the pressure, you increase the temperature. Common sense tells you when you expand and you get the work out of the system, you lose temperature, you lose pressure. So at point 4, you should have a lower temperature, much lower temperature and much lower pressure. Just simple as that. If you have a crazy answers, then you're in deep trouble. Now, this is accurately 52.4% efficiency. However, let's say this is on your test. And as you notice, there are 3 areas that you need to interpolate. That takes a lot of time. So you need to make assumptions. If you make your right assumptions within a ballpark, what do you get? You're going to end up with 51. Or you're going to come up with 50.4. Guess what? That's acceptable. Or you come up with 53, or maybe even 54. That is still acceptable. But if you get a crazy number like 10 or 99%, then you made a wrong assumption. You understand that? Now, do you have any questions before I go to the next step? Okay. Once again, key to this problem, number 1 key was CP and CV were variables, vary with temperature. We could not use the heat transfer equation. That would have been much easier, much faster to do that. Fortunately, we couldn't do it. Now, there are other examples that we're going to do that CP and CV are constant and see how easy we can get it done. Any questions?
Professor, I had a quick question. I was just curious, like, is this like this example you gave us, is this similar to an automobile's like compression ratio and temperatures? Or if not, then what is closer?
No, this is totally not similar to the automotive engineering.
Okay,
Because auto cycle was not created to drive a car with it. It was created to basically generate power. And once they saw that by changing two processes, they can do that, then that's where the diesel came in and just blew everything out of, out of water or whatever you want to call it.
got it.
And
So we have better processes than this now.
came out with a real cycle.
Got it.
That's Brayton or gas turbine. Those are two real cycles. This is somewhat ideal. Stirling cycle, Ericsson cycle, it's very similar to this. That's why we're not going to cover it, just waste of time. So they didn't achieve big deal. Again, this 52% is not real either. There are so many other things involved that you see in the future that will bring this number down to about 30% or even 29%. That would be the actual real auto cycle.
Got it. Thank you.
Not a problem. Any other questions? Now, before I get to diesel cycle, let's talk about assumptions that I'm talking about. Let's say you have a T2 of 246 degrees. No. 671 degrees Kelvin. And you're trying to find the value of H2. So you're going to go to the table and you don't find this number. What you find is 670 value. The next one is 675. For instance, these are all examples, it's not real. Don't quote me on that. So what you're going to do, you say, okay, at 670, I have a H2 value of, for instance, 685 kilojoule per kilogram. At 675, my H2 value is 692 kilojoule per kilo. So what would be my assumption for 671? When I look at it, 671 is closer to that number, right? I need to pick a number between 685 and 692. If I pick 691 as an assumption, I made a mistake because 691 is this way, it's closer to this number. So what do? I make an assumption that this is going to be equal to 687 kilojoule per kilogram. And then what I do, I said, assuming H2 is equal to 687. And you're in good shape. No interpolation, nothing. That saved 5 minutes of your time. 2 minutes of your time. And if you have to do it 3 times in one problem, that adds up to about 8 to 10 minutes of your time that you have to go through the interpolation. This way, it takes only 10 seconds or 30 seconds to do it. Much quicker, much faster. However, if you don't write assuming, if you don't write that, and I'm assuming this number, you're telling me this is an accurate number. Since it's not, you're in deep trouble. So every time you make an assumption, you need to learn that. This is what we do in engineering. We always state our assumption. So you state your assumption that I assume the value of H2 to be that. Then you're okay. Because first of all, you are within a ballpark figure. You did your best to find a number closest to that. You're great. You're home free. Who cares what is the actual value of H2? Because at the end of the day, once you find the efficiency, you're off by a little bit. And we don't care. So in this course, please do not hit your head against the wall to come up with accurate answer. Accurate answers are not, absolutely not important. What was important, you saw the processes that I wrote down, step 1, 2, 3, 4, all that. If you just write all the processes that you would have taken in order to find those, without any numbers at all, just writing your process, you get 50% credit of that problem. Because to me, it's important to see that you understand what's going on. To me, it's not important whether you can use your calculator or crunch a number correctly or not. I don't care. I care about your engineering thought process. In the future, when you graduate, nobody cares how quick and how fast you can crunch the numbers. Everybody's looking for your thought process. Start learning that and start doing that, rather than like a old Western movie that 2 guys were getting in front of each other. Whoever draw the gun faster, gonna kill the other guy. Whoever draw the calculator faster and punch the number, gonna get a big credit. That's not gonna happen. Trust me. You will notice it when you take the first test. I can tell the one who spent a lot of time doing a lot of number crunching, and at the end, they got nothing. Because they were focused to just crunch the number, feeling careless about the process. And those are the ones complain, well, my numbers are pretty close. Why aren't I getting a credit for that? You need to show me how did you get those numbers? Because tomorrow when you become an engineer and you go in front of a client, you send a memo to them, here's what it is. They said, okay, how did you do that? Where did you get from point A to point B? They don't care about answers. Last semester, I caught 4 people that they cheated. It was so obvious that they cheated. They have all the numbers correct and all the processes were wrong. And when I confronted them, the number one question, well, I have all the right answers. I don't care. Where did you find this number? how did you find this number? They couldn't answer. I had to tell you, 4 people got stuff from school. They can never, ever become a mechanical engineer. Their history. If they go to any other school to start again, first thing they're going to ask, what is the transcript? And the transcript says that with the MAE2, due to the cheating, they're out. They're being expelled. No other universities will touch you. Unless you go and start from scratch and studying like economics or forensic, no, I don't know, something, but not an engineering, not civil, not electrical, not mechanical, not chemical, nothing. You're out. Those 4 people destroy their career by doing it. So please be aware. I've been doing this for 28 years and I have 37 years of experience. I can tell who has studied, who's got a good head on his or her shoulder, and who tried to cheat and cut the corner. No matter how smart you are, you cannot pull a fast one over my head. I've seen all kind of crazy things. So please, don't make an attempt. All right, so this is what I was talking about, how you can make assumptions. Any questions? It's very easy and simple, but make sure you write your assumption. Now,
Professor,
yes,
when you made the assumption of finding the enthalpy for the H's, you said at 670 degrees Kelvin, it was a 685, right?
this was just arbitrary numbers.
Oh, okay. I thought they were, because I looked at
told
the
you,
table.
No. I have no table in front of me. I was just trying to cross a point. That's how you can make the assumption.
Oh, okay, thank you. Okay.
None of those numbers that I had here was accurate.
Okay. All right.
I just came up with those bogus numbers to prove a point, not to give you the accurate answer.
Okay. Thank you.
No problem. Any other questions? Now, the next topic is the most important one. It's diesel cycle. A genius from Denmark named Rudolf Diesel was working in a lab. He came up with some idea. He got a tube. He put a little piece of a cotton in that tube. Then he put a little piston at the top of it, in that tube. Nothing else. And then what he did, he pressed that piston coming down. As soon as he pressed that and pressurized the air within that tube, that piece of cotton caught on fire without any fuel, without any ignition. That was a genius way, and that's how he came up with the diesel cycle. It was unbelievable. So that's the whole concept that it started, and he built the diesel cycle based on this very simple concept. Once again, diesel cycle, we start with compressor, This is air. Going at point 1, coming out at point 2, coming to the combustion chamber, adding fuel. By the way, somebody asked me, because diesel engine uses diesel fuel, is that why they call it diesel engine? No, it's the other way around. Once the diesel engine was started, Rudolf Diesel came up with an idea that we can refine the crude oil. Instead of finding the gasoline, which has a very low flash point, I don't need that. We can do a less processing, less refining, and find another fuel between crude oil and gasoline and use that, because I pressurize the air so much that I don't need gasoline. I can use another fuel. And that's why they named that after Rudolf Diesel. They call it the diesel fuel. If you get a gallon of diesel fuel, pour it on the, sidewalk, light a match, throw at it. It's like lighting a match and throwing in the water. Nothing's going to happen because it's got a very, very high flash point. And that's the beauty of, his, genius idea. Because if you do the same thing with gasoline, you match, you light the match, you're going to catch in fire when you light it. Because the fume of gasoline will just do that. Very low flash point. If it's jet fuel, you're dead. Your whole body's going to burn. So he used heavier fuel, and that's why diesel fuel are more efficient and they go longer distance, because he's compressing the heck out of the air going to the combustion chamber, and diesel fuel need that compressor to burn very easily in a combustion chamber. So coming out at point 3, then going down, this time we call it diesel engine. And finally, that's our cycle. We keep getting fresh air all the time, keep exhausting it, from that part. So that's our cycle. Once again, this is work in, Q in, work out, and this part is our Q out. You saw this in Carnot cycle, Otto cycle, diesel cycle. Equipment arrangement remain the same. What changes? The process. Let's see the process. Process 1 to 2. What did we say? Compression, expansion, always isentropic. That will never change. Isentropic, compression. Process 2 to 3. This is what he changed in the Otto cycle. Process 2 to 3 It's isobaric heat addition, meaning P2 is equal to P2. Isobaric means constant pressure. Then process 3 to 4. What do we have before? Isentropic, that will never change. Again, isentropic expansion. Process 4 to 1, similar to Otto cycle. Isochoric heat rejection. These are the 4 processes. As you notice, the difference between this and Otto cycle is just only one process. Everything else is the same except that. And that made a huge difference. So-
Professor, so is the second process is isobaric and the fourth process is isochoric?
Isochoric, isobaric.
Got it. Thank you.
Sorry. Isobaric, isochoric. Heat addition. Another question? So now that we have a new processes, we should have new TS and PV diagram. So let's do, if you don't mind, I'm going to erase this equipment because you don't need that. You've seen that so many times, plus the processes are there. So that's a TS. Right next to it, PV. Process 1 to 2. 1, 2, isentropic. Process 3 to 4, isentropic. So that's the tier side. Now, the other one is a little different. Process 2 to 3, isobaric. 2, 3. Process 4 to 1 is constant volume. 4 and 1. So connecting them, this is that's isentropic part. That's the PV diagram. Now, in diesel cycle, we don't care about TS diagram because it's not going to help us solving a problem. What's going to help us is what is happening here on the PV diagram. So now, let's see that this would be the work in, that would be the Q in, that is the work out, and this is the Q out. So let's find various energy values on the cycle. Work in, isentropic, that's H2 minus H1. Q in, constant pressure, that's H3 minus H2. work out isentropy, H3 minus H4. Q out is isochoric, constant volume, U4 minus U1. These are the values. As always, Q in minus Q out will give us net or work out minus work in. As I mentioned before, this will never change. Net work is the difference between heat in and heat out, or work out and work in. Thermal efficiency never changes. Net work divided by Q in, or 1 minus Q out, or Q in. That will never change. All cycles, chapter 9 and 10. We also have, in this case, mean effective pressure, like we had before, which is a network divided by V1 minus V2. So that's these characters. Finally, in diesel cycle, we have R of V, which is a compression ratio. We will have relative volume at any given point. We have one thing that no other cycles have, and that is called cutoff ratio. Now that, it's something that it's very interesting. I want to discuss that in details next time. And then we do some examples of the diesel cycles, and you'll see the difference between the diesel cycle and others. So for now, we use PV diagram. These are the various values. As you can see, everything's a delta H, except the last one, which is isochoric. Otherwise, everything is delta H. Network and thermal efficiency and MEP remain the same. We still have a compression ratio, and we still have a relative volume. There is one more thing we need to talk about, and we're going to talk about it next week. Now, before you leave, we have 36 students. Is Mr. Lai still here? Okay. Out of the 36 students, we're going to divide the class to 7 groups. 6 group of 5 and 1 group of 6 for the project. What I need next Wednesday, because Monday is holiday, when you're coming back on next Wednesday, I need 7 volunteers to be the project team leader. And I don't need all of them to be boys. We have few ladies in our class. Please make sure that you volunteer yourself. If you don't, I will volunteer you. So I need 7 names beginning of the next class for the project, so I can forward the project to you guys, make the assignment, and you can start working little by little until the deadline, which is a few days, 10 days before the final exam. Okay? Have a good holidays. I'll see you Wednesday. Don't forget, 7 volunteers to be a team leader. That's one of the practices you're going to need for your future.
And Professor, you just want us to come into class ready, or do you want us to send an email to you?
No. When you come to the class, I get all those 7 names. I'm going to write them on the board, and then we'll decide what we're going to do next. First thing first. Any questions?
So next class meeting's on Wednesday, right? Because of Labor Day?
Yes.
Okay.
It's a Labor Day holiday, so I'll see you next Wednesday. For those of you who have additional questions, want to talk to me in the office hours, stay, and the rest of you have a great holidays, and we'll see you next one.
Thank you, Professor.
Have a good one.
Thank you.
Have a great weekend, Professor. Thank you.